There are infinite numbers between 0 and 1. There are also infinite numbers between 0 and 2. There would more numbers between 0 and 2. How can a set of infinite numbers be bigger than another infinite set? I think the problem is you are thinking of infinite to be a very big number. It is not a very big number, it's a different kind of thing. A similar problem exists with 0, in that it's not just a really small number, it's actually 0. For example, if I take a really small number like 0.00000001 and double it, I get 0.00000002. If I take 0 and double it, I still get 0. 2x 0 is not bigger than 1x 0. If I have an infinite number of numbers between 0 and 1, then they are separated by 0. If I double all of those numbers, then they are separated by 2x 0, so they are still separated by 0. This is the answer I understood the most. Thinking of infinity not as a group of numbers but as something entirely different in the way that 0 is entirely different was the metaphor I needed. People kept using an example where you divide a number by 2 or something and it kept losing me. Like, yes, you have one of those numbers in 0-1, but you have both of them in 0-2, meaning you have more, regardless of how you arbitrarily divide it. But thinking of infinity as a different concept outside of a series of numbers helped tremendously. Thanks for this. The thing which helped me wrap my head around it, as much as I have, was when it was explained to me that infinity is not a number. Being infinite is a property of a set. So if you consider it as a different property, like blue or hot, it makes more sense. You can't count to blue, and whether one set is bigger than another doesn't affect whether it is blue or not. Here's a way to see that they are the same size. We're going to show that for each number between 0 and 1, there exists a number between 0 and 2, and vice versa. Pick any number between 0 and 1. Multiply it by 2. You now have a number between 0 and 2. Vice versa, pick any number between 0 and 2. Divide it by 2. You now have a number between 0 and 1. This works both for the case of rational and real numbers. We just constructed a so-called bijection between the intervals 0, 1, and 0, 2. Your intuition for size comes from the structure of intervals, rather than the amount of elements they have. The intervals 0, 1, and 0, 2 have the same quantity of points, because you can pair them up. However, the interval 0, 2 is twice as long as the interval 0, 1. The particular elements within 0, 2, and their relation to each other is what gives it that length, not the amount of elements. I think his intuition comes from the fact that the world is discrete in practice. You have 2x more atoms in 0, 2 cm than in 0, 1 cm. If you are not looking at something made of atoms, let's say you have 2x more Planck lengths in 0, 2 cm than in 0, 1 cm. See what I mean? Ops intuition can be correct for physical things in our world, but mathematics go beyond that, with rational numbers being infinitely divisible. As soon as there is a limit to how much you can divide things, even if it's 1 million digits after the decimal point, Ops intuition is valid. The concept of size that's used for infinite sets is basically this: two sets are the same size if you compare the members from one up with the members of the other with no leftovers. You can do that with the two sets OP asked about, so they're actually the same size. But you can't do that with the set of all integers and the set of all numbers between 0 and 1. Well, two things are happening here. There are different kinds of infinities, some of which are larger than others. However, the number of real numbers between 0 and 1 is the same as the number of real numbers between 0 and 2. You can prove this second one by creating what's called a bijection, showing that for every member of group A there is exactly one member of group B. This is easier to show with another set, but it does carry over into this situation. Let's say we're comparing every even number with every even and odd number. It seems like the second one should be larger, right? But if we take every even number and divide it by 2, we go from 0, 2, 4, 6, to 0, 1, 2, 3. That second set sure looks like the set of all even and odd numbers. The same thing applies here. If you take every real number between 0 and 2, and divide them all by 2, you get every real number between 0 and 1. There is also a way to show that some infinities are larger than others. This one is a bit harder to picture, but imagine a list of every real number between 0 and 1. This is every rational number, but also every irrational, every transcendental, every number that is between all of those forever. It's not obvious how you could sort such a list, but let's say you just write down the numbers randomly. Well, this is a list that you can order 1, 2, 3, etc. Sure, it's infinite, but so is the list of counting numbers. Right now there's no obvious problem. If they're both infinite, you're good to say that they're the same size. However, we can do something that breaks this. Let's create a new number. The rule is that it's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on forever. This is definitely a real number, meaning it should be on the list, but it's definitely not on the list, since it's different from every number on the list in at least one place. Even if you added this new number to the list, you could just do this again. What we've done is shown that, even if we use all the counting numbers, all infinity of them, we can still create numbers that are not on that list and for which there is no matching number. There are numbers left over after we've used all the counting numbers. Even though they're both infinite, there are more real numbers than there are counting numbers. It makes no sense to me at all, but it's an interesting read nonetheless. The rule is that if you can match up each number of two sets 1, 1, then sets have to be the same size. For example, the set of whole numbers between 1 and 10 is the same size as the set of even numbers between 2 and 20. Why? Because you multiply each number in the first set by 2 and you get exactly the second set. 1 gets matched to 2, 2 get matched to 4, and so on. In the same way, the infinite 0, 1 set matches the set 0, 2 by multiplying each number by 2.